All right, hello everybody. It's Mr. Merrifield here. I'm going to post some review topic stuff for you guys, but I also wanted to give you some resources because I know it's been a while since we've done this. So this week chose exponents, especially with all that news in the media you see with like COVID-19 curves. You'll see these kind of like exponential curves graphed. And so this is one of the things we really want to understand because it comes up in so many different places. So we're going to start with kind of the basics. So I'm just going to start with the definition of an exponent. What is it? Why is it important? But essentially, an exponent is just specifying repeated multiplication. And I'm going to ground this in something that I think will make it make a little bit more sense. So if I think of what is multiplication in the first place, well, multiplication is just repeated addition. So if we look at how do we build multiplication, well, you can have something like 3 plus 3 plus 3 plus 3 plus 3, and then we say, well, we have this quantity that's basically adding 3 each time in a pattern, and this may be a pattern that keeps continuing. Like the next day, you would add 3 again. The next day, you add 3 again. So an easier way to do that is just write 3 times 5. We have 1, 2, 3, 4, 5 groups of 3. And you can see if this is something that was scaling up, like on day 1 it was 3, then you add 3, then you add 3, and you've got a certain x number of those. You just represent that as 3x. Well, what if I had a different pattern? What if I had a pattern as the such where each time I would multiply it by 3? So like on day 1, I had a value of 3, but on day 2, it tripled. On day 3, it tripled again. On day 3, it tripled again. Well, I could just represent that as an exponent, which is just repeated multiplication. So I could say that's 3 times itself, 1, 2, 3, 4, 5, 3 to the 5th. And we could see if we had this unknown number of how many 3's did I have, and we did that x times, it would just be 3 to the x. And so basically how I define this is I have a base, which is essentially what am I multiplying? So here the base is 3 because I keep tripling each time. And then I have an exponent. And that tells me how many times do I multiply. And especially if you have a system that's sort of changing over time. So for instance, if it was like figuring this per day, we could specify how many. We could see how it changes over time. So let me finish this off with how many times do I multiply? And we've got our definition of an exponent. So what we're going to kind of do is go through the rules of exponents. We got a bunch of different rules that allow us to kind of work through these quickly, work through these efficiently. So we'll start with a definition of the product property. So we're going to use this example. We used it earlier in the year, but I think it's a good one. So essentially, we're going to try to develop the product property for this. And we're going to look at it kind of an old school way, and then how we do it a little bit more efficiently, an algebraic way. So what I'm going to start with, so I'm just going to look at the question. So we got the average weight of a newborn caribou. So we got the newborn is 2 to the 3. So let's just write that down. A newborn is 2 to the 3 pounds. And then it says, on average, an adult male caribou weighs up to 2 to the 6 times as much as a newborn. So essentially what this is asking is if I take a newborn and I multiply it by 2 to the 6th, I should get the weight of an adult. So a newborn baby caribou is 2 to the 6th times as heavy as an adult. So one way I could do this is I could say, well, a newborn, we specify that's 2 to the 3, and I got to multiply that by 2 to the 6. So one way we could do it is we could do this the super old-fashioned way. So I'm going to separate these into colors so you can really see what we're doing. So we'll do 2 to the 3rd is in blue, and then we'll do 2 to the 6th, that's in red. So if I look at this, I can say, well, 2 to the 3, we just defined that. That specifies that I've got to take 2 multiplied by itself 3 times. So I can write that as 2 times 2 times 2. We'll bring this little multiplier down. We can do the same thing with 2 to the 6. The base is 2, the exponent is 6, so that's telling me 2 times 2 times 2 times 2 times 2, oh, exhausting, times 2. So you can already see if I had like 2 to the 80, this would be an exhausting method, but we'll just condense it back down. So we got the same multiplier, 2 times 2 times 2 times 2 times 2, and if we count them all up, 1, 2, 3, 4, 5, we'll get all the way to 9. There are 9 2's, that's how many times 2 is multiplied by itself. So this all condenses down to 2 to the 9. However, what we can see is I just counted up how many reds, 1, 2, 3, 4, 5, 6, counted up how many blues, 1, 2, 3, and so essentially what I did is I took how many 2's are being multiplied here, how many 2's are being multiplied here, I added them all up, and I just condensed it down into one exponent. So essentially what I was doing, if I have the quantity 2 to the 3 times, well, actually we'll keep the 2 in blue, 2 to the 6th, that is the same thing as 2 to the 3, and we'll do plus 6, which gets us the same thing, 2 to the 9. You have to work it all out this way. This way you can just shortcut it. So now, essentially, we got our product property, and I'm just going to call it product property. So essentially, we can like shortcut this and say, well, if we have something with the same base, but a different, actually, it doesn't even matter if the exponents are the same or not. So we'll say a to the b times a. So I'm being very explicit saying these have to have the same base. I can't do it if they're not the same base. So if we have a to the b times a to the c, I can just condense that down and say, well, that's the exact same thing as a to the b plus c. So we could use this very quickly, and I could say like, well, if I have 3 to the, just make up a number, 60 times 3 to the 4th, I don't have to do this way and list out 3 times itself 60 times and 3 times itself 4 times. I can just add those exponents together when it multiplies, because we see when we work it out the old school way, it's just adding these exponents up. So I get 3 to the 64. And that would be a quick application of that property. So let's now take a look at what happens when I have a power to another power. So we're going to do this kind of the same way. We're going to look at an old school method, a new school method, and then we'll figure out a shortcut. So we got the power of power properties, or what happens when I have something that's already an exponent and I raise it to another exponent. So I'm going to take this 5 squared times 5 to the 4th, and I'm going to expand it out kind of like the slow old way. So if I look at this and I just look at this outside exponent, I can say this is essentially 5 squared times itself 4 times. So essentially, I've got 5 squared times 5 squared times 5 squared times 5 squared. And I could even separate it out further, and I can say, well, this is 5 times 5. This is 5 times 5. But I don't even have to do that. What I can do instead is I can use that product property that we just went over. Fix that in a second. My board's not as good at home. So what I can do is I can say, well, if this is multiplied by this, by this, by this, we can just use that property that we just learned right here. And we can say that this is 5 to the 2 plus 2 plus 2 plus 2. If we call back all the way to the beginning, let's just use that property that addition is the same thing as, or excuse me, repeated addition is the same thing as multiplication. And we can say that's just the same thing as 5 to the 4 times 2. Essentially, we have 1, 2, 3, 4 2s, so I can say 4 times 2, and that's going to be 5 to the 8th. And you didn't have to do that. You could just add up the 2's 4 times, but you'll see why I'm kind of illustrating that in a second. Because what we did, we had this 5 squared to the fourth is we essentially represented this as repeated addition to say it's multiplication. So noticed I took the 4 times the 2, so I can just write that as 5 to the 2 times 4. I can take this exponent here, I can bring it in, and I can multiply. So we can just condense that down, 5 to the 8th. So I wanted to represent the sort of power, two-way power of an exponent property. That's what we'll call it here. I can just say in generalized form, if I have something that's a to the b to the c, that is the exact same thing as a to the b times c. So just take a quick example of how this will work. If I say something like a to the 100 to the fourth, well, I don't have to go through this really annoying way. I can just use this property here and say that's the same thing as a to the 100 times 4. And of course, that simplifies down. This is an operation we can just do. 100 times 4 is 400, a to the 400. And we've got our power to the power property. All right. Another one we want to review is what happens when we take an exponent and we divide it by another exponent. So this will be our quotient property. Quotient, we're just talking about division. So what happens when we take a quotient of two exponents? Quotient right there. So what I'm going to do here is I'm just going to represent this out as a fraction. So if this is a division, it's the exact same thing as writing this as a fraction. So I could write this as 6 to the 5th over 6 cubed. So I'll write that here, but I'm going to write this again just kind of in our expanded out form. So I'll take this and I'll write the top 6 to the 5th, so that's 6 times 6 times 6 times 6 times 6. And then on the bottom, I've got 6 cubed, or 6 to the 3rd power. And I've got 6 times 6 times 6. All right, so what I'm going to do is I'm just going to cancel out. So remember, if I have something like 5 times 3 over 5, I can just cancel across and say, well, that's just 1 over 1. And that becomes 3 times 1 over 1. And then that just becomes 3 over 1 or 3. Use that same property down here. So if I have a 6 in the numerator and a 6 in the denominator, that's just like the operation of multiplying something by 6 and then dividing it by 6. So they undo each other. So I can cancel any pair out. So cancel one pair. I've got more pairs to cancel though, so I'll continue. 6 by 6, 6 by 6. And you'll notice what I have left in the top is just 6 times 6. So this is the same thing as 6 times 6 or 6 squared. Let me write that too because it's not so good. 6 squared over 1, which is just the same thing as 6 squared. Anything divided by 1 is just itself. However, you can see that I just took away how many 6's they were from the top and canceled it out from, or excuse me, how many 6's I had in the denominator, cancel them out from the numerator. So essentially what I did was I just took away everything that was in the numerator and took away any pairs I had in the denominator, which is essentially subtraction. This is the same operation as 5 minus 3 here to get 2 left. So what I can do with the exponents is I can simplify it and say, this is just the same thing as 6 to the 5 minus 3, which, of course, 5 minus 3, quick integer operation, 6 squared. So what I can do now is I can make a nice property here. So I'm going to write it in two ways. One, if you see it in a fraction. One is if you see it as division. If I have something like a to the b divided by a to the c, and again, I'll write it two ways. I can write this as a to the b divided by a to the c. That just gives us a to the b minus c. And so to look at an example like this, let's take something that we wouldn't want to do in the first method. We definitely want to take this new quotient property here. Let's take something like a to the 100 divided by a to the 47. So if I did that, I could just use my quotient property here of say, well, b here is 100, c here is 47, and I could just say that's a to the 100 minus 47. And what I get from that, 100 minus 47, that gives me 53, a to the 53. So didn't have to go through all of this really hairy process of writing a times a times a times a all the way till I got 100 a's and then writing out 47 here and individually canceling them all out. I can just use this quotient property here, simplify that exponential right on down. So a couple more things I want to cover. Next, we're going to cover a case that students will find kind of confusing. And so what happens when we raise it to the 0 case? So it's extremely tempting to say that a to the 0 power is 0. It is not. Not true. Not at all true. No. So let's take a look at an example. So we're going to look at kind of what happens when we scale down our exponential. So we've got this card game, and essentially what this card game is doing is they're matching sort of the exponential form to the standard form. So standard, just think simplified out. So you look at what, I believe this is pronounced Marcella, whatever you want to call her. So essentially you're matching out 3 squared, just 3 times 3 is 9, 3 cubed, 3 times 3 is 9, times it by 3 again, you get 27, 3 to the 4th, 81, and they're matching them up. So we'll start with our 3 to the 4th, and we know an exponent, or we know 3 to the 4th in exponential form. We could just simplify that down, multiply 3 by itself 4 times, and we would get 81. 3 cubed, she has matched that to 27. 3 squared, we've matched that to 9. 3 to the 1, that's essentially just writing 3 once, so that's just 3. And so we look at what's happening is essentially each time we go down this table, we're just descending down, we're dividing by 3. So if I do this operation, I get 3 to the 4th minus 1. Essentially, you're dividing 3 to the 4th, dividing it by 3 ones, which is the same thing as subtracting 1 from the exponent. Ignore those, they're just mismark. And I get 3 cubed. And I can keep doing the same thing along. I'll just write this as 3 to the 1. So divide off by 3 to the 1, divide off by 3 to the 1, divide off by 3 to the 1, and I got all the way down. And 3 to the 1 we know is just 3, so same thing on this right-hand side, just dividing by 3. And we look at what happens, so we got to get to this last column. So let's look at it on the simplified form right here. So if I take 3, this follows a very specific pattern, which is I take the right-hand column, I divide it by 3. So I'll divide this by 3 as well. And essentially I get 1. 3 divided by itself is just 1. And then I'll do the same thing over here, and I'll write it in my exponential form. Instead of dividing by 3, I'll write the same thing but in exponential form. Let's divide off by 1 power of 3. And I get 3 to the 0. So what this proves is using this pattern of exponentials, I've basically proved that 3 to the 0 is equal to 1. And so I can simplify this down and say this actually, if we do this with any number, any exponential, it does not matter. It could be it could be 1,000, it could be 100,000, it could be -6. No matter what my base is, if that's raised to 0, it's 1. Another way to think of this is, let's say I look at the number 7, and I say, well, I've got the number 7, it's just hanging out, and I ask you, look at this number. How many powers of x does it have? And you say, well, it's got no powers of x. Or essentially, we could say that as well, 0 powers of x. So I could say this is the same thing as 7x to the 0, because x to the 0, the x applies here. I essentially get 7 times 1. I get right back to the starting point. So if I get anything to the power of 0, it is 1. And just as a quick example of that, let's do 1 billion to the power of 0. That's just 1. So we've got our 0 exponent property. So there is one last example that I would like to show you all, which is our negative exponent property. So take a look at one more example. If I get my slides going, there we go. So let's take a look at this example where instead of just descending all the way down to 0, I'm going to descend even further. So what happens when we get a negative exponent? So one way I can do this is, let's just represent that as a fraction really quick. For the third, divided by 4 to the fifth power, and we'll work this out. 4 times 4 times 4. It's going to be divided by 4 times 4 times 4 times 4 times 4. All right, so we're going to use that same strategy we looked at with this quotient property here, where we just took away pairs of 6s in the top and bottom. This time we're dealing with 4s, and we're going to cancel them out so we don't have any pairs left. So multiply by 4 and divided by 4, that's essentially a null operation, just gets you back to 1. And we do that again and again. So in the top, just to be very specific, this isn't 0 up here, it's 1. So there's nothing left, there's no multipliers left over except keeping it intact. So there's just a 1 up here. And in the bottom, I'm left with 4 times 4. But what I'm also going to look at here is there's something special about this property. So 1 over 4 squared is also equivalent to a negative exponent. So what if I used the quotient property on this? So remember, our quotient property was a to the b divided by a to the c. That's going to be equal to a to the b minus c. And we're going to apply that here and see what happens. So I'm going to take this, and essentially I've got 4 cubed divided by 4 to the fifth, and I can write that as 4 to the 3 minus 5. And so essentially what I'm looking at here is 3 minus 5. It's going to go into the negatives for the negative 2. So what this is saying is essentially when I have a negative exponent, that's saying like divide the number by 4 twice, or 1 over 4 multiplied by itself. So we can say from this is 1 over 4 squared is equivalent. It's the exact same quantity as 4 to the negative 2. So what I can write on this is our negative exponent property. If I have something like a to the negative b, that's equivalent to 1 over a to the b. And it also works if there's a negative exponent in the denominator. So conversely, if I had something like 1 over a to the negative b, I could say that it's exactly equivalent. And I'll put a little divider because these are separate. So if I have 1 over a to the negative b, I can say that's the same thing as a to the b. And so we'll look at a couple examples on this. I think I have them. Oh, I don't, but I'll just copy them on here. So if we look at a couple examples on this, I'll copy it onto the page really quick. So let's look at what happens if I have something like 8 to the negative 2. I can just write that as 1 over 8 squared, or the same thing as 8 squared is just 64. And conversely, if I had something like 1 over, let's go, I don't know, 3 to the negative 3, I could say that's the same thing as 3 cubed over 1, but essentially I don't need to write something with 1 as the denominator. I can just write that as 3 cubed, which is equal to 27. All right, hope this was beneficial. I'll post some more next week as well, and probably like a follow-up assignment. But what I'm going to do for now is I'm going to set your guys' Prodigy accounts to kind of review some exponential properties. I'll also try to post some other kind of supplemental stuff. So if this was helpful, please let me know, and I'll keep making these because I think they're kind of fun. And then I guess that's kind of it. So you guys have an excellent rest of your day. Hope you guys are doing okay, cooped up inside. And I hope to see you all back real soon. Take care.